Understood. So imagine we start with a rod which is uniformly charged, and we have done this question already before, but we can just do it in a different perspective. So from the center to the point P, the distance is smaller. This is center. So electric field we know for due to point charge we give as kq by r square. So when you make an elementary charge, a small charge, by cutting a part of some big continuous charge, so you can have d equals to k dq by r square,
Yes, sir.
and then you apply the integration to get the net field. So can you do the calculation and find the net field at point P using this simple definition?
Okay.
Try this out.
So,
Yes.
sir, I'm getting KQ by R minus L by 2 into R plus L by 2.
Correct. That's the right answer. So you know this answer, right? So this is a very famous answer. So now the problem with integration is you can apply integration only when because see we are trying to find a vector quantity called electric field strength. So first of all, we need to realize that E is a vector; it's not a scalar. And integration refers to addition of values. So we just add something. So we cannot integrate vectors. That's the first rule. You can only integrate scalars. Okay. So to integrate vector, the rule is they can be integrated only when that the direction is same, or else we can integrate their components but not the vector as a whole. So that is the whole idea. Now to understand the basic meaning of this, let's say we have the another example. So now earlier the charge were at axial position of the rod, that is along the length of the rod. So what if we don't take the axial position as the location? So what if the charge is the point is not on this line, rather I choose a point somewhere here. So if I choose the point somewhere here, and then I'm calling the point is at a distance, let's call it D from the rod. D is the perpendicular separation between the point and the rod. So we can see clearly the point P does not lies on the axis of the rod. It is somewhere different. And I am assuming it to be in front of the rod somewhere at random location. And if I join this point to the edges or the ends of the rod, so this we can call as alpha and beta.
Sir, I'm not able to hear you.
Am I audible? No?
Now you're audible, sir.
Okay. So what I'm saying is that the point P is located in such a way that the ends of the rod at the point P subtends an angle alpha and beta. So alpha and beta are the angles subtended at point P by the ends of the rod, and D is the perpendicular separation between the point P and the rod. So that's things, these are the things given to us. Now if I choose, let me redraw this diagram separately. So we again draw the same D. First of all, we must draw the D. That's the rule. And the point is P. And you can extend this line, and we call this as a reference line. So these are some basic things about derivation. So you first of all we draw a perpendicular to the rod, and then we call it a reference line. The next step is if I choose a small part of it somewhere here. So then this part will create an electric field somewhere here at this point P, right?
Yes, sir.
So now we can call this as DE because this is the charge dq. And the way to assume the location is this. So we can call this height from the reference as y, and the width or the thickness we call is dy. So that's how we assume. And this angle we can call as a general angle theta, because eventually I want to express my answer in terms of alpha and beta, so I have to choose theta. Now if I keep on selecting such elementary along the length of the rod, what about what will happen to D? Will the direction remain same or direction will change?
Sir, it will change with the elementary particles.
Yeah, correct. So we can understand the direction is not a constant here, and therefore such vector cannot be integrated. So we cannot integrate it. But at the same time, we can just convert this into two components, and one we call it DE perpendicular to the rod, another we call DE parallel, and this will be DE cos theta, and this will be DE sin theta. And what we can realize that no matter which elementary you choose, everyone will have only two components, one parallel and one perpendicular. So now we can integrate each component separate because they will have the direction along the fixed line. So now you cannot integrate D because the problem is the direction is not fixed. But we can integrate a D perpendicular because it is always towards right or left in worst case. And D parallel will be either below or above, but not in any other direction. So as long as the directions are parallel or anti-parallel in that way, we can integrate the components. So first of all, if I call this radius as R, can you find the D value using Coulomb's law? I mean this formula, KQ by R square. So here they give you lambda as the linear charge density. What is lambda?
Linear charge density.
Just like the linear
Q
mass
by
density. Yeah. So in this case, it's a uniform. So we can write as dq by dy. So can we write a dq as lambda dy?
Yes, sir.
And r is something not known to us. Rather, I want answer in terms of theta. So can we relate r, theta, and d because d is a fixed value? It's given to us.
Sir, cos theta is equal to d by r.
Yeah. So r is d sec theta. Sorry, r cos theta is d. So d sec theta. Yeah. So eventually r becomes d sec theta, correct? After rearranging
Yes,
and all. Now you can see we have brought the variable theta somehow in the expression, but dy is something which we are not interested. The reason is simple. I want my answer in terms of theta only. So we can write tan theta equals to y by d. So y equals to d tan theta. And now I can differentiate with respect to theta both sides. It will give you sec square theta. And this will help us in eliminating dy in terms of theta. So we can eventually write like this.
yes,
So dy is equal to d sec square theta d theta. And therefore, the d becomes k lambda dy upon r square, which we can now rewrite as k lambda, and dy is d sec square theta d theta, and r square was d sec theta whole square. And if you simplify this, it's very simple formula. It's k lambda into d theta by d. Correct? So you can see this is a simple answer.
yes, sir.
A lambda d theta by d. That's something very simple in terms of appearance. Now, what I said, although this is the formula for d, but we cannot integrate this one to get the answer. Why? Because this is a variable in direction. This is the only magnitude part, right?
Yes, sir.
So to get the d perpendicular, we can, because we know we can integrate this one. So d perpendicular is equal to how much?
D cos theta.
Cos it. So now you can see this is k lambda by d cos theta d theta. So this is actually integrable. This is actually integrable. And the theta, now the question is how to put the limit. So now we come back to the formula. And this is diagram.
Minus beta to plus theta.
Very good. Minus beta to plus alpha.
Sorry, plus alpha. Yes.
And now this will give you a very simple and nice answer. Sine alpha plus sine beta. Eventually.
Yes, sir. So you wrote plus beta there. Sir.
Yeah, so my okay, sorry. My bad. So E perpendicular is equals to A lambda by D sin alpha plus sin beta. Similarly, can you derive the form for E parallel? Because
Yes,
this
sir.
is E sin theta, so you can do it. Yeah.
So
Yes.
I'm getting k lambda by d into cos beta minus cos alpha.
Correct. So now you can see we have a negative sign. And now see, this is these are the components. So the net electric field, in this case, I may write like E perpendicular, let's call I cap or E parallel minus J cap, just for the sake of writing. So the net field is basically a vector sum of this. So to find the modulus of the net field, we can write as under root of square of these two, right?
Yes.
And if you do the square, then you will get the formula for the net field. So can you do the square and tell me the formula? How much it is coming?
Okay. So sir, I'm not able to hear you.
Yeah, tell me. Sorry. Yeah.
Sir, actually for the E parallel, I was getting minus cos beta minus cos alpha. So
No, no, cos of minus theta is cos beta only.
yes, sir.
So the integration of sin theta is minus cos theta, no?
Yes, sir.
So I can take minus also cos alpha minus cos.
Oh, right. Yes, sir.
Okay.
So, sir, I'm not able to hear you again.
Yes, yes. I don't know why it is getting locked up.
Yes, sir. Sir, are you speaking now?
Am I audible?
Yes, sir. Now
Maybe
you're audible, sir.
10.
Sir, I'm getting 2k lambda by d into sine of alpha plus beta by 2.
Very good. Now there's something interesting here.
So can I just join through another device? My
You are
sister is
seeing this?
having a class
Yeah,
right
yeah,
now.
no problem. No, no problem. No problem. Yes. Go
Okay.
ahead. Am I audible to you? Hello, am I audible?
Yes, sir.
Great. So now what you can see the answer as the total angle is how much?
So alpha
Alpha
plus beta.
plus beta. So this is called the total angle subtended at the point P. So what we need to realize that the net electric field is 2k lambda by d into sine of angle subtended by 2. And not only that, in fact, the direction of the resultant is also along the direction of angle bisector. So direction of EP is in the direction of angle bisector. Okay.
Okay, sir.
Now we can prove it. It's not something that we cannot prove. So let me show you how to prove it. If we have a rod, if we have a rod and this is the charge, and if we choose some random point P, this was the reference line, correct?
Yes, sir.
And the net field we got here is one right, another left. I mean, other down, right? So this is the direction of resultant field, right? Let's do it something like this. So if I call this angle as some angle, let's say phi. So phi is how much? So that's easy to find. So tan phi equals to tan phi is how much?
Sir, y by d, or yeah, e perpendicular by, sir, e parallel by e perpendicular.
So this is basically k lambda by d will cancel out. So what we have is cos beta minus cos alpha upon sin alpha plus sin beta, right?
Yes, sir.
Now we can apply the compound angle. I mean, this what is half angle formula, the cos c minus cos d formula, and cos c minus cos d is how much? You know, two
Sir, 2 cos, sorry, 2 sine
sine
c plus d by 2.
into sine
C minus d. Sorry,
c
d
minus
minus
c.
c by 2.
Yeah, this is
Yes,
like
sir.
alpha, and sine c plus sin d is 2 sine c plus d by 2 into cos c minus d by 2. So you can see this will cancel out. So what will left with is tan alpha minus beta by 2. So the phi turns out to be how much? So I'm assuming alpha is bigger than beta in this case. That's why the field is downward. So now if this is the phi is alpha minus beta by 2, okay, and this whole angle is alpha. So this angle is how much? That's called delta. So delta is basically alpha minus phi,
Yes, sir.
and this will become actually alpha plus beta by 2. So you can see the delta is exactly alpha plus beta by 2, the angle bisector.
Yes, sir.
So although the diagram is not reciprocating the same y, but that's true. So now we have proved mathematically that the resultant always bisects the angle subtended by the rod at the point P. That's the whole idea. Okay.
Okay, sir.
So it will have many nice consequences. So for example, if I tell you that we have a rod which is some length maybe. So plus 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 plus. So let's say the charge is here Q and length is L. So lambda is not given, but you can find the lambda indirect. Okay. And
Yes,
now
sir.
I'm asking you that can you find the electric field at a distance L from the bottom edge at point P?
Okay, sir.
Or maybe I can take as uh, okay, L by root 3. That's easy.
Sir.
Yes.
Oh,
Tell me.
sir, just a second, sir. I didn't see that you changed it to L by root 3.
Root 3. Yeah, yeah, yeah. So just you need to find this angle. That's it.
Yes, sir.
So this is the total angle subtended by the rod.
Sir, I'm getting root 3 by 2 KQ by L square, sir.
Okay, correct. So the theta terms are how much? This is 1 by this is root
60
3.
degree.
60
Yes, sir.
degree. So EP we can write the maximum 2k lambda by d sine 30 degree, correct?
Yes, sir.
This k lambda by L by root 3. Because sine 30 is half of cancel. So root 3k U by L square, correct? This is the answer.
Yes, sir.
Okay. Or if you try to solve by the component method, it will be a bit lengthy only. So the E perpendicular will be k lambda by d, and then sine alpha plus sine beta, but alpha is only theta, so this is sine theta. The other angle is missing, right? And E
Yes.
parallel k lambda by d, and we can just write as cos theta, because that's only one angle given. And because this is the perpendicular, so always remember the line which is perpendicular will be taken as a reference. So angle is taken from the reference only, not anybody else. Okay.
Okay, sir.
And then of course, if you square and add, this will become EP becomes k lambda by d itself, right? That's it. Nevertheless, So imagine we have a situation in which the rod is here. So let's say we have a lambda, and the point is here. So you can see the point is not facing the rod; it is somewhat on the extended part of the rod. So you need to extend the rod to draw a perpendicular, right?
Yes, sir.
So in such situation, when you have to extend the rod, the ends of the rod will make some angle, but on the same side of the reference, right?
Yes, sir.
So if I call from the, because I said, as I said, the angle we try to measure from the reference only, let's call this is D. And if I call this angle as alpha, the bigger angle we take as alpha, smaller I am calling as beta. So the component wise answer will change. So E perpendicular becomes k lambda by D. And because we had the sine theta as an integration from earlier, it was minus beta 2 plus alpha. Now it is plus beta 2 plus alpha.
Yes, sir.
And this was k lambda by d cos theta and minus again it's the same beta 2 plus alpha. So we can see the answer will change slightly. It becomes sin alpha minus sin beta, but this will remain same because the cos will have no effect of plus and minus.
Yes, sir.
So this was actually minus sin beta, the same thing. So in case of extended part, the only difference is the sign of the perpendicular component will change, and therefore the net of formula will be same 2k lambda by d sine of angle subtended by half, like
Alpha minus beta.
right. So now this is easy to remember that it is half of the angle subtended, right?
Yes, sir.
Okay. Just
Okay, sir.
so now we can solve a variety of problems, and the most important is called the infinite rod. So infinitely long uniformly so if something is infinitely long, so no matter which point you choose will divide the line into two halves,
Yes, sir.
and the upper half is at infinity and the lower half is at infinity. So the angle becomes how much?
Sir, tends to 90 at both the sides, sir.
Correct. So this is a tends to 90 on both sides. This is one way of thinking, and therefore the EP becomes 2k lambda by d itself, because sine 90 plus sin 90 is 2.
Yes, sir.
So you can do by various methods. If you choose the perpendicular, then parallel will cancel out because both are equal angle, and in parallel component we have difference because we have on two different sides, but the perpendicular component will add up because they are on the two sides. So the whole answer is net answer is towards the direction which is perpendicular because of simplicity, and the answer turns out to be 2k lambda by d. if we have semi-infinite, so if we have so now if the infinity is on the one side, the angle subtended we can take as 90 degree.
Nine. Yes, sir.
So the resultant will be bisector of this, which is 45 degree,
Yes, sir.
which also means the two components are equal in value, right?
Yes, sir.
So whether we talk about the perpendicular one or the parallel one, so for semi-infinite, these two components are equal, and that is always equals to k lambda by d and k lambda by d itself.
Yes, sir.
Because one angle is, so you can think beta is 0 and alpha is 90. And even if you apply the formula, you get the same answer. Or you can think in terms of total angle subtended, and that is 90 degree. And so the answer is 45 degree. This is the EP. And because both components are equal, so the net field will be root 2 k lambda by d. Or if you use the formula, which is 2 k lambda by d sine angle subtended by 2, so it will again give the same answer. So there are many approaches by which you can think of. And there is a very interesting feature that if I choose this answer as the starting point to derive the formula of the infinite wire. So every infinite wire we can think as a two semi-infinite wires, correct?
Yes, sir.
And we know both semi-infinite can create its own field.
Yes, sir.
So I can say that the upper half will have a contribution on the right and below, right? So
Yes, sir.
upper half will create right and below, but the lower half will create a right and up, correct?
Yes, sir.
And therefore, you can see clearly the up and down will cancel out, and the right will become twice, two times. So the net value at point P is again two eyes of the single arrow, and every arrow represents k lambda by d. Because this is k lambda by d, this is k lambda by d, this is k lambda by d, this is k lambda by d. So you can see on the right side it will add up,
Yes, sir.
and the parallel component will cancel out. And so that's for obvious reason, because the upper half will try to push and the down will push in such a way the parallel component will nullify. So there are many ways of thinking about the same problem, and sometimes such kind of thinking helps us in getting the answer without putting a lot of effort. So
Yes.
imagine we have a situation.
Sir, can I just come back in a minute, sir?
Yeah, sure.
Answer.
Yes. So imagine we take an infinite wire, but at the same time I bend this into, I mean, at right angle. So this is infinity, and lambda is the linear charge density. And now I'm looking to find the electric field at a angle bisector somewhere here. So in fact, I can make any general point, not let's say. Okay, what is the question is what is the electric field at a point x comma y in vector form? I want to know E vector and coordinate is given x comma y. So what will be the answer?
Okay, sir.
Maybe very cumbersome, I don't know, but this just I created this problem.
Okay, sir.
So I think I need to help you. Right? So what you can do is,
Just
yeah,
a second, sir.
okay, fine.
So,
Okay, tell me.
sir, I'm getting the E perpendicular value as 2k lambda by d into sine alpha minus cos alpha, considering alpha to be
Yeah,
uh
understood.
yeah.
So the idea is it's a kind of not so easy because this distance is, if you look carefully, this is x, but this
Yes,
is
sir.
y. So the d for the first wire is x and for the other wire is y. Okay, so what we can do is let's remove this part from the consideration. So don't consider this part as of now. Just think of the remaining part. So for this is like semi-infinite, and we know the answer for the first semi-infinite. I can call it 1, 2, 3, 4. So the E1 will create electric field right and down, and the 4 will create up and left. Can you see that?
Yes, sir.
Basically, they cancel out each other. So it
Yes, sir.
means there is no role for the rest. So this is as good as finding the electric field at a point P at the corner of a rectangle.
Um,
Okay. So now I can call it only 1 and 2. Let's call this is 1. This is 2. So 1 will create the you can just take it right and up, and maybe, and the 2 will create right and up only. So the right will I mean you can just add. So this is like E parallel of 2 and E perpendicular of 1, and this is like E parallel of 1 and plus E perpendicular of 2, like this. So basically they get added together. So parallel, and so we have to do it separately, and it's a really cumbersome. But this is the whole idea. Like the first we create a two component right and up. So again, if you want, you can divide into two parts. You can write take one separately and find the answer at the point P, and then you can add the other part separately, and then you can add the value because they will have direction that we know. Okay.
okay, sir.
So this is really a lengthy question, but this is how we break down the question into a simpler problem, and then we get the answer. Okay.
Yes, sir.
Let me give you some doable problem. This is like you can do at home. So imagine if you have a problem like uh, two infinite wires. Now this is easy because both are infinite. So I'm not taking same infinite, both are infinite. And one I take as x-axis, other I take as y-axis.
Sir, that means wires overlap, right, sir?
No, this is without touching, just crossing it. Doesn't matter.
Okay, sir.
Then this is like passing over. This is like bridge, a small bump. You can think this.
Yes, sir.
So if I call this as x-axis and if I call this as y-axis, then if I choose any point P, and if I again call the x and y, now this is easy problem because these are infinite. So the the vertical will create the field, right?
Yes, sir.
and the bottom will get up. That's it. So the net field at a point P in vector form you can attach E1 I cap and E2 J cap, and the value of E1 is simple 2k lambda 1 by x, and E2 is how much? 2k lambda 2 by y. That's it. Okay.
Yes, sir.
So the net field at a point P we have is 2k lambda 1 by x I cap plus lambda y j cap. So questions like this you can create, and not only one, you can create a large variety of them just with the help of. So imagine this is a very nice problem, and the problem is yeah. So imagine we have the x and y coordinate, and we have a semi-infinite wire which begins from the x-axis somewhere on the x-axis. Let's call the a comma 0, and it goes to infinity at an angle theta. Lambda is the linear charge density. We are supposed to find the net field at O. Only value I want. So what is the net field at O?
Sir, is it 2k lambda by a sine theta, sir?
So it is 2k lambda by a sine 2k. Yeah, I think so. I think so. Something close, but not exactly this. Something you're missing. What is the
Sir,
angle subtended? What is the angle subtended? Do you know? The angle subtended by the rod at O. So
right.
one line is parallel. You have to draw a parallel line because the infinity means it will meet at parallel.
Yes, sir.
So parallel means this is also theta.
Sir,
So the
I was
angle,
more of going like
so you wrote
it's
the
a
right answer. Yeah, one part, but what you just missed the angle subtended part.
oh,
The rest is
sir,
right.
it's a semi-infinite wire, sir.
But the O is not at the edge. Where is O?
And no, sir, like is this a
Yeah,
semi-infinite wire or a
yeah, yeah.
infinite wire, sir?
Same infinite. It begins from
Oh,
somewhere and goes.
okay, sir. Sir, I consider it as an infinite wire.
Okay, okay. Then that's the right answer.
Okay, sir.
So change the
Sir,
answer now.
yes, sir.
Go ahead.
So,
Yes.
sir, now I'm getting k lambda by a cos theta by 2, sir.
Yeah. So that's correct answer. So the better way of writing k lambda by a sec theta by 2, right?
Yes, sir.
Yeah. So because the angle subtended is theta only, right?
Yes, sir.
And the d is a sin theta.
Yes, sir.
So we just need to extend this line, and so extend the line, and we draw perpendicular. This is a, and the angle subtended is theta only. This is the right answer. Okay. So now we are going to do the calculation of electric field intensity due to uniformly charged circular arc uniformly charged circular arc at the at its center of curvature. So we are supposed to find the, so we have a any arc which is part of some circle, so we can call it circular arc, and it is uniformly charged, and we are supposed to find the field at the center of curvature, which means the center of the circle of which this arc is part of. So from symmetricity, can we say the net field will be along the angle bisector?
Yes, sir.
So no matter how small the arc is, the net field is going to be at bisector. And in fact, now there is a rule for any line charge, whether it's a curved line or a straight line, the net field is always in the direction of angle bisector. The rule is only true for the uniformly distributed charge. So if I call the entire angle as alpha, then this will become alpha by 2. Now, how to solve question when we have a circular arc, how to choose the reference? So the simple answer is always take the line of symmetricity as the one axis, and you can draw perpendicular to this line, and you can choose x and y. That's it.
Okay, sir.
So the net field is going to be y direction. So we are only supposed to find the y component, not the other component. Okay.
Yes, sir.
So the way of taking references for circular arc, we move theta and we cut d theta, right?
Yes, sir.
So we can call this as theta. This is the d value. So the net field we can, okay, so D is easy to write, but we are looking for dy, which is d cos theta, and now it's simple. So d will be k dq by r square because r is constant here. This is pretty easy to solve and derive. So dq we can write as
Sir,
lambda
yes,
r d theta,
yes.
and if you solve, it's k lambda by r cos theta d theta. So net field is equals to, so now the angle we have to take is from where to where? The limit
So
of integration.
minus alpha by 2 to alpha by 2.
Very good. So this is the same answer. 2k lambda by r. So instead of d, we have r sine alpha, the half of the angle subtended. That's it. Same formula.
Yes, sir.
So the only difference is the d is now removed by or replaced by r, and the angle subtended is easy to write. So we can extend this formula for any arc. Arc may be quarter circle, arc may be semicircle, arc may be full circle. Okay.
Okay, sir.
If we take uh, quarter is, we'll do it for quarter because quarter is very famous. So So imagine we have a quarter ring of charge is lambda. We know this is 90 degrees, so the resultant will be at 45, which means it will have equal x component and y component.
Yes, sir.
And because the net value we know, net is 2k lambda by r sine 90 by 2, which is root 2 k lambda by r. So basically, each component is k lambda by r and k lambda by r. That's the beauty of a quarter. It's just k lambda by r will be each component. Okay. So
Okay.
this is something similar to the semi-infinite wire. K lambda by d, k lambda by d. So a quarter circle behave as semi-infinite wire, and similarly a semicircle. If I choose a semicircle,
So are you speaking something?
no. Now again the same question. So here you can look carefully. We can think this as two quarter circle. So the right quarter will create a field left and down,
Yes.
and the left quarter will create a field right and down. So right left will cancel out. So net field which will remain is down only, and that is also logical because that is the angle bisector, right?
Yes, sir.
So the net field in this case will be downward only. And two arrow means if you know the answer of one arrow, this will be twice of the k lambda by r. That's it, right? It is clear?
Yes, sir.
Or you can derive from basic by taking the elementary integrated from 0 to pi, or you can do the way you want. So once you know the answer for the circular arc and the answer for the wire, we can combine these to create some more problem. So for example, so imagine we have a x, y, and z axis. This is y axis, this is x, and what I'm drawing is like a heart shape object. So it looks like a heart in diagram, but it is basically a circle. Can you see the circle?
Yes, sir.
And this circle is in which plane? Y z plane.
Yes, sir.
If I draw another circle, and this is in which plane?
Sir, XZ plane.
X z plane. Correct. So now you can see there are two circles which looks like a heart shape in by default diagram. And let's put some charge, and you can call it lambda or whatever. So let's call it lambda 1. This is lambda 2. Okay.
Okay, sir.
I assume the radius is r only. So radius is r. So the first ring will create the net field downward like this,
Yes, sir.
and the second will create the net field left.
Yes, sir.
So we have to write here vector form. So we can write as 2k lambda 1 by r minus j cap, and 2k lambda 2 by r minus I cap. So you can see that 2k by r we can take common. So lambda 1 minus j cap, and lambda 2 minus I cap. And so the net field is 2k by r under root of. So we can create a variety of questions in 1 dimension, 2 dimension, or 3 dimension. Always make sure that you break into small pieces which is easy to derive, and then superimpose the answer. That's the whole idea of solving tough question. So we will see more of such question in the next lecture. Okay. And we'll
Okay.
proceed to other derivations. So this is not a difficult part, but yeah, it is just a beginning, and we'll see more derivation coming soon. Okay.
Okay, sir.
So you may try some question from there, because the questions like this is not given. This is what I create in the class only. So you need to wait for some time. Okay.
Okay, sir.
Good question from this.
Sir, in which book can I start solving the questions, sir?
I'm going to share the sheet. So the sheet, I think I have shared the sheet. Sheet.
Sir, no, sir, for electrostatics you haven't shared.
Just a minute. Let me share first. Then we can do it. Just a minute. Electrostatics. Yeah. So for this chapter, we will stick to resonance sheet only. Okay. And we'll
Okay,
finish
sir.
we'll finish the SQ row first for sure, but then we have to solve from this book also. So here it is.
Okay, sir.
It's gone now. So you can go to the maybe exercise 1. You can do the section A and section B at least now. Yeah, A and B part. From the part 1,
Okay, sir.
part 2, and exercise 1, part 1, part 2 both. Okay,
Yes, sir.
just A and B part, and then from from exercise 2 you can also do. Uh, okay, they are mixed. This is mixed question. No, don't do this. Only exercise 1, part A, part B, and then everything depends on the potential and the Gauss law and various things. Okay, fine. So now you can start doing from this. Okay.
Okay, sir.
Good night. Take care. So we will keep next lecture from again back to evening 6 p.m. Okay.
Okay, sir. Yes, sir.
Okay. Yeah, fine. Good night.
Thank you, sir. Bye, sir.